Hey guys! So last time I saw you, we were talking about non-Mendelian genetics, and specifically looking at sex-linked inheritance or sex-linked traits. Now we didn't get to finish that conversation, so I made a slideshow about sex-linked inheritance, and I'm going to spend some time actually going through that slideshow with you. Now, what I posted here for you are some slides. This is the student copy. And you'll notice there are some spots with red, like spaces. As I'm going through my presentation, feel free to go through this one and actually fill in the information. Wherever it's red and there's a space, that would be something that you can fill in. What I'm going to do, though, is actually work through the student copy teacher copy that I have here. Okay, so we're going to talk a bit more about sex-linked traits or sex-linked inheritance. And this is what we call the X's and Y's of genetics. And we'll find out here in a bit what that actually means. Why do we call it the X's and Y's? Okay, so when we're talking about Mendelian genetics, we already talked about this in class a bit, but this is surrounding that scientist Gregor Mendel and his discovery through his research with pea plants. So what he found was a clear pattern of inheritance in which all offspring are affected equally. A big part of his theories was this law of dominance, where some alleles are dominant and will actually mask or cover up the recessive alleles. So our big capital alleles cover up our small lowercase alleles. And we've seen this through our Punnett squares. Now, in non-Mendelian genetics, it's not that simple. Okay, non-Mendelian genetics, which is most of genetics, are inheritance patterns that do not follow all of those laws or conclusions that Gregor Mendel came up with. Okay, in some forms of non-Mendelian genetics, we have where there isn't a trait that outweighs the other. They might blend together. And, there's a bunch of different patterns for how a trait can be inherited. So what I actually have done is I've posted a PlayPosit in our page for today. I suggest if you would like to learn more about non-Mendelian genetics and all the varieties, well, some of them anyway, to go through that PlayPosit. Okay, what we're going to focus on, though, is sex-linked inheritance. So with sex-linked inheritance, we're talking about sex chromosomes. Okay, as a reminder, humans have 23 pairs of chromosomes, 46 in total, but 23 pairs. 22 of those pairs are what we call autosomal chromosomes. And if you were to look up the definition of this, you'll find that autosomal chromosomes are those numbered chromosomes other than sex chromosomes. Now, our sex chromosomes, those are either X chromosomes or Y chromosomes. Okay, and the genes that are located on these are considered sex-linked genes. We're going to be talking a lot about these two different chromosomes and how those genes are sex-linked. Now, what do these X and Y chromosomes look like? Well, here's an image of a karyotype. And we've seen karyotypes before. This is more of a drawing. But this still shows us our 22 autosomal chromosomes, all of the genes on them, and these sex chromosomes. And here we can see that there's this possibility of having an X and a Y, or two X's. Now the X and Y sex chromosomes, they carry genes that will determine your biological sex. So I want to again reiterate that we're talking about biological sex and not gender. Okay, identified gender is very different than biological sex. Now, individuals who have a combination of X and Y sex chromosomes, they are grouped or often referred to as males. Okay, individuals with two X chromosomes, they are grouped together as females. Now, it's very possible, and I find this interesting, I don't know if you guys will, but it's very possible that in the sex chromosomes that we have, that it won't look exactly like this. Some people have more than one, or more than two chromosomes. And that would be due to some type of mutation, some type of error that happened in cell division. Now, you're not really going to find where they have less than the two. Often when that happens, the offspring doesn't end up living, but it is very possible that people can have more than two X's. You can have people with two X's and a Y, or three X's even. So that is one of those errors that do tend to happen sometimes. So what really is this difference between the X and the Y chromosome? So here we have an image of an X chromosome and a Y chromosome. And we can see that the X chromosome is much bigger than the Y chromosome. So size is a big difference. If you look deeper than that, you can see that there's also different types of genes and different number of genes on both of these chromosomes. What I really want to point out is this right here, this SRY gene that's on the Y chromosome. This SRY gene is considered the male determining gene. This gene is what's going to help a male actually develop into a male, develop those physical characteristics that we associate with males. Now, if an individual doesn't have a Y chromosome, they're going to develop as a female. But if they have a Y chromosome and this gene is mutated to where it doesn't work, then they will also develop as a female. So it's possible to have an X and Y and still have female characteristics. So just one of those interesting things that I didn't learn about until I took advanced anatomy that I figured I'd share with you guys. Okay, so here's what these sex chromosomes look like. And if we have an individual with both an X and a Y, remember, they would be grouped in as male. Okay, they would be considered male. Okay, so before we move on with all of the different types of inheritance, let's take a stab at this Punnett square. So let's look at how these sex chromosomes are inherited through fertilization, and so what the probability will be of there being a male or female produced in pregnancy. And we're going to actually do that. Oh no. Using, oh my goodness, I like lost everything for a second, sorry. Using our whiteboard. Okay, so here's our whiteboard. And I'm going to set up our Punnett square. Okay. So we're going to cross two parents, both a mom, a female, and dad, a male. Now, I'm telling you that sex-linked inheritance is different than, say, than Mendelian genetics, but there's a lot of similarities. When we are performing this cross, we're still going to perform the cross like we would with Mendelian genetics, where each of these alleles for mom and each of these alleles for dad have an equal probability of producing an offspring. To show that, we're going to first take mom's alleles, and sorry, I'm calling them alleles, we'll technically call them her first sex chromosome. Taking our first sex chromosome, and we're putting them in the two boxes below her. And we'll do the same with her second X chromosome. Okay, so her first X chromosome has a 50% chance of being included in the offspring that's produced. Her second X chromosome also has a 50% chance. They have an equal chance. Same thing with dad's X and Y. Okay, so we have two possibles up here with his X chromosome, and two possibilities for the offspring with his Y chromosome. Okay, this leads to the formation of, or two possible formations for XX individuals, which would be known as female, and I'll just put an F here to show that, and two for X and Y, which we would know as male. Okay, 2 out of 4, so that's a 50% chance for there to be a female produced in pregnancy, and a 50% chance for a male to be produced in pregnancy. Again, just looking at sex chromosomes, so just considering biological sex, not technically gender identity. Now, this whole pattern might look very similar to what we learned in Mendelian genetics. So why is it different? Well, the big difference here, and we'll talk more about this in a second, is that males have a Y, and males have one Y chromosome and only one X chromosome. Females don't have a Y chromosome. So we have a difference in chromosomes that's going to cause a difference in the probability for us to get certain linked alleles, linked disorders between males and females. So we're going to build off of this Punnett square that we made and looking at specific alleles on the sex chromosomes. We're looking at specific genes and specific alleles.